Chapter 1.4 Inverses. Inverse functions are a special class of functions that undo or reverse each other. The inverse of a function y equals f of x is denoted y equals f superscript -1 of x if the inverse is a function. The -1 is not an exponent because f represents a function, not a variable. Vertical line test / horizontal line test. If you drag a vertical line across the graph from left to right and it intersects a graph more than once on the line, then the graph is not a function. We learned that in Math 10C. You can use the horizontal line test on a relation to see if the inverse of that relation is a function. So if you drag a horizontal line across a relation and it intersects a graph only once at any point, then the inverse of that relation is going to be a function. To determine the inverse of a function, we interchange the x and y coordinates. For every x value, there should only be one y value so that the inverse is a function. Example, let f of x equal the coordinate points 2, 3, 3, 5, 4, 7, and 5, 9. Then f inverse x would be, to determine the inverse of a function, we interchange the x and y coordinates. So here we have x is 2, y is 3. Interchange those for the inverse. Then we have the first coordinate would be 3, 2. The second one, interchange x and y, we get 5, 3. Third one, interchange x and y, and we get the point 7, 4. And last one, interchange x and y, and we get the point 9, 5. And we see that each of our x values, 3, 5, 7, and 4, only has one y value. Obviously, since none of our x values repeats, it's only going to have one y value. So that means it is a function. Example, consider the graph of the relation shown. On the same grid, sketch the graph of the inverse relation. So remember, we switch the points of the x and y for the inverse. So for this graph, this point here is the point -6, 0. So the point on the inverse function would be 0, -6, which would be there. Then this point on the original function is -4, 4. Switch the x and the y, that gives us +4, -4 for the inverse relation. This point x is 0, y is 4. Switch the x and the y, that gives us 4, 0 for the inverse relation. This point is 2, 2. Switch the x and the y, we still get 2, 2. So we'll have a point there for the inverse relation as well. And last point is 2, 4, 6, 2. Switch the x and the y, we get 2, 6. That's on the inverse relation. Join the points of our inverse relation, so from 0, -6 to 4, -4. From 4, -4 to 4, 0. From 4, 0 to 2, 2. And from 2, 2 to 2, 6. Part B, state the domain and range of the original relation and its inverse. For the original relation y equals f of x, we have the domain is x such that the lowest value of x is -6, is less than or equal to x, is less than or equal to the highest value is +6, xer, or in interval notation, it would be from -6 to 6, so -6, 6. Both of those endpoints are included, so square brackets for both. The range for y equals f of x is y such that the lowest y value is 0. The highest y value is 4 and yer. In interval notation, it'd be 0, 4. Both of those endpoints are included, so square brackets for both. Then for the inverse, which we don't know if it's a function, so to write an inverse of something that might not be a function, we just switch x and y, so x equals f of y. Our domain is x such that the x values go from 0 to 4. 0 is less than or equal to x, is less than or equal to 4, xer. Or in interval notation, 0, 4, both ends are included, so square brackets. The range of the inverse relation is y such that the y values go from -6 to 6. -6 less than or equal to y, less than or equal to 6, yer. And in interval notation, -6, 6, both ends are included, so square brackets. Notice that the domain of the original relation, -6 to 6, is the range of the inverse relation, and the range of the original relation, 0 to 4, is the domain of the inverse relation. C. Are both relations functions? Explain. The original relation, which we'll call f of x, passes the vertical line test. If we take a vertical line and we shift it anywhere left to right, it's only ever going to touch one location at a time, so that is a function. But if we take a vertical line and put it on the inverse relation, we touch more than one spot here, here. So anywhere, if there's any point where you touch more than one spot at a time with a vertical line, then it's not a function. So no, y equals f of x is a function, but its inverse, x equals f of y, is not a function, since it doesn't pass the vertical line test. D. The graphs are reflections of each other about the line y equals x. Are there any invariant points? Let's draw the line y equals x. So that's where x and y are equal, which would be at 0, 0, at 1, 1, 2, 2, 3, 3, etc. And -1, -1, -2, -2, etc. So this is the line y equals x. So inverse relations are reflections of one another across this line. We can see this if we take a point and we count how far away it is from the line. So this point is 1, 2 diagonal away from the line, and the point that it corresponds to on the inverse is 1, 2 diagonally away from the line. So the point 0, 4 becomes the point 4, 0, which is just a reflection across the line y equals x. And we see this for all of our points. This point here, 6, 2 on the original function, diagonally 1, 2 away from y equals x. Diagonally on the other side, 2 away from y equals x is our transformed point. The point 6, 2 on the original relation becomes the point 2, 6 on the inverse of that relation. So are there any invariant points? Remember that invariant points are points that are the same after the transformation. When we have a reflection across a line, invariant points are any point that is on the line of reflection. For our original relation, we have one point that is on the y equals x line, the line of reflection, and that is 2, 2. So that will be an invariant point, and we see that because it's on both the original function and its inverse. 2, 2 is on the line of reflection y equals x. Therefore, the point 2, 2 is an invariant point. Graph y equals f of x if y equals the square root of x. So graph y equals square root of x is what it's saying. We can plug in some values for x. If x is 0, the square root of 0 is 0, so we have a point at 0, 0. We can't have negative x values because we can't take the square root of a negative. So we're going in the positive direction. If x is 1, the square root of 1 is 1. X is 4, the square root of 4 is 2. If x is 9, the square root of 9 is 3. Then we can join those points with a curve to get the graph y equals the square root of x. We'll mark our points. That was 0, 0. This was 1, 1. This was 4, 2, and 9, 3. A. On the same grid, sketch the graph of the inverse relation f inverse x. Remember, for inverse relations, we switch the x and y values. So I can plot the same points, just switch my x and y's. 0, 0 would still be 0, 0. 1, 1 would still be 1, 1. 4, 2 would become 2, 4. And 9, 3 would become 3, 9. Then I can attach the points with a curve to draw the inverse relation. And I know this is a function because it passes the vertical line test, since this is continuing to get wider. So it's never going to go straight up and down. So anywhere along there, I'm only going to have one intersection at a time with a vertical line. Then this is y equals f inverse x. B, state the domain and range of the original function and its inverse. For y equals f of x, we have domain is our lowest value is 0, so x such that 0 is less than or equal to x, and then the graph continues going to the right, so it goes to infinity, so less than infinity. Or if we write that in interval notation, we have 0, infinity, zeros included, so square bracket, infinity we never get to, so round bracket. And then for the range of f of x, y, such that the lowest y value is 0, is less than or equal to y, then the highest y value would be infinity. It does continue rising forever as it goes to the right, even though it looks like it kind of flattens out, but it will continue going up forever, just going up slowly, so less than infinity. In interval notation, we write that as 0, infinity, square bracket on the 0, round bracket on the infinity. The inverse function y equals f inverse x. The domain for that function, the lowest x value is 0, so 0 is less than or equal to x is less than. It is going to continue going to the right as it goes up, so it's going to continue to infinity just slowly, so less than infinity. In interval notation, that would be 0, infinity, square bracket on the 0, round bracket on the infinity. And then for the range, again, the y value would have a minimum of 0, is less than or equal to y, and then it is continuing up forever, so going to infinity, so less than infinity. Or in interval notation, 0, infinity again, square bracket on the 0, round bracket on the infinity. So in this case, domain and range were the same in the original function. Then when they switch in the inverse function, they're still the same because they were the same to begin with. C, the two graphs are reflections about the y equals x line. Are there any invariant points? Invariant points are on the line of reflection, which is y equals x for inverse relations. So the points that we have that are on y equals x, 0, 0, and 1, 1 are invariant points. They're both on our line of reflection, which would be here. And we can see that those points are on both graphs. Restricting the domain. Consider the function f of x equals 4 minus x squared. A, graph the function f of x. 4 minus x squared, we can write that as negative x squared plus 4. That is an a value of -1, so a reflection across the x-axis, and then a vertical translation up 4. Y equals x squared is a quadratic with a vertex at 0, 0. It looks like this. we're going to reflect that down and then shift it up 4. So if we reflect it down, the vertex would still be 0, 0. Then we shift that up 4, and it would be here at 0, 4. Y equals x squared has a point at negative 1, 1. We reflect that down across the x-axis, then it would be at negative 1, negative 1. And then we translate that up 4 units, 1, 2, 3, 4. So it would be here at negative 1, 3. Y equals x squared has a point at 1, 1. We reflect that across the x-axis, then it becomes 1, negative 1. Then we shift that up 4, and it becomes 1, 3. Y equals x squared has a point at negative 2, 4. Reflect that across the x-axis, it becomes negative 2, negative 4. Then shift that up 4 units, it becomes negative 2, 0. And quadratics are symmetrical, so we have a point at positive 2, 0 as well. Y equals x squared has a point at x equals negative 3, y equals positive 9. Reflect that across the x-axis, we get negative 3, negative 9. Then shift that up 4 units, and we get a point at negative 3, negative 5. And then quadratics are symmetrical, so we have a point at positive 3, negative 5. Then we can draw our function f of x. Part B, graph the inverse of f of x on the grid. Is the inverse a function? We can decide right now if the inverse is a function. If we do the horizontal line test on f of x, we see that it's going to fail the horizontal line test, which means that the inverse of f of x is not a function. Since f of x fails the horizontal line test. We could also wait until we've drawn the inverse and then check if that passes the vertical line test. Let's graph the inverse. I can either switch the x and y values of each point and then graph that point, or I can reflect across the line y equals x. Either one is fine, it doesn't matter. I'm going to draw the line y equals x and reflect across that. So this point is 1, 2 away from our line. So go 1, 2 on the other side, and it's going to be at the point 4, 0. And if I had switched the x and y values, that point started as 0, 4, and it becomes 4, 0. This point is 1 diagonally from y equals x. So on the other side, diagonally 1, we get a point at 3, 1. This point is 1, 2 away from the line of reflection. On the other side, 1, 2 away, we get a point here at 3, negative 1. This point is 1 away from the line of reflection. Go 1 on the other side, and we get a point at 0, negative 2. And this point is 1 away from the line of reflection. Go on the other side 1. We get a point at 0, 2. This point is 1 away from the line of reflection. The other side 1 away. We get a point there at negative 5, negative 3. And last point, this one is 1, 2, 3, 4 away from the line of reflection. Go 1, 2, 3, 4 away from the line of reflection on the other side. We get a point at 5, 3. Then we can join those points together to get our inverse. And because it's not an inverse function, we can't call it y equals f inverse x. We have to call it x equals f of y. Because if we use the other notation, that represents an inverse function. This notation represents an inverse relation. C. Describe how the domain of f of x could be restricted so that the inverse is a function. So how can we make it so that f of x could pass the horizontal line test? If we take a horizontal line, we see that we touch on 2 parts. If we were to split this f of x down the center on the axis of symmetry, and we just had either this part or we just had this part, then the inverse would be a function. Because if we just had one side, then if we took and did the horizontal line test, we would pass the horizontal line test. So restrict the domain of f of x to x has to be greater than or equal to the axis of symmetry, which is x equals 0. So x is greater than or equal to 0. Or we could do x has to be less than or equal to that value. So we're just getting 1/2 or the other in order to make the inverse of f of x a function. Because then our inverse would be either just this half, which is a function, or it would just be this half, which is also a function. It's when we have these 2 halves together, that's when we fail the vertical line test, and then the inverse is not a function. If f is a function with domain A and range B, the inverse function, if it exists, because it says function, not relation, is denoted by f inverse x and has a domain of B, which is the range from f of x, and a range of A, which is the domain from f of x. If the inverse is not a function, it can be represented by x equals f of y. So we can only use the notation f with the -1 of x if the inverse is a function. Otherwise, we have to write x equals f of y for the inverse. Determining the equation of the inverse. When working with an equation of a function y equals f of x, interchange x for y, then solve for y to get an equation for the inverse. Example, algebraically determine the equation of the inverse of each function, verify graphically that the relations are inverses of each other. A f of x equals x squared plus 1. We can write this as y equals x squared plus 1. Then for the inverse, we switch x and y, so we have x equals y squared plus 1. Then we need to isolate the y, so we subtract 1 to get x minus 1 equals y squared. Then we need to square root both sides, but we don't know if y started as a positive or a negative, so we have to do plus minus. square root. So we get y equals plus minus the square root of x minus 1, which gives us two things to graph. We have y equals positive square root of x minus 1, and also the other part of the graph will be y equals negative square root of x minus 1. Let's graph these, starting with f of x equals x squared plus 1. That is y equals x squared translated 1 unit up. So y equals x squared has a point at 0, 0. That will now be up at 0, 1. It also has points at negative 1, 1 and 1, 1. Those will be translated to negative 1, 2 and positive 1, 2. It also has points at negative 2, 4 and 2, 4. So those will be translated to negative 2, 5 and positive 2, 5. And then y equals x squared has points at negative 3, 9 and positive 3, 9, which will be translated up to negative 3, 10 and positive 3, 10. So I can draw the function f of x equals x squared plus 1. Then I can draw the inverse relation y equals square root of x minus 1 and y equals negative square root of x minus 1. I'll start with y equals positive square root of x minus 1. The radicand cannot be negative since we can't square root a negative. So x minus 1 has to be greater than or equal to 0, which means x has to be greater than or equal to 1. So we get the first value of x equals 1. The square root of 1 minus 1 is 0. So x equals 1, y equals 0. If x is 2, 2 minus 1 is 1. Square root of 1 is 1. So we get a point at 2, 1. Then we want the radicand to equal perfect squares. If x is 5, 5 minus 1 is 4. And the square root of 4 is 2. So I get a point at x equals 5, y equals 2. And if x is 10, 10 minus 1 is 9, and the square root of 9 is 3. So I get a point at 10, 3. I can draw that portion of the inverse. And then for the negative portion, it's just a reflection of the positive portion across the x-axis. So we'd still have the point that's on the x-axis at 1, 0. Then the point 2, 1 is reflected down to 2, negative 1. The point 5, 2 is reflected down to 5, negative 2. And the point 10, 3 is reflected to 10, negative 3. Then we can draw the bottom half of our inverse relation. So this portion is y equals positive root x minus 1, and this portion is y equals negative root x minus 1. Then we want to verify that these are inverses, so we can look at either each of the points and see that the x and y values are switched, or we can look at the line of reflection, y equals x. The vertex of y equals x squared plus 1 is half a unit away from the line of reflection, and half a unit on the other side is that point on the inverse. This point is half a unit on above, and this point is half a unit below. This point is 1.5 units above, and then go 1.5 units below, and we get to this point. This point is 1, 2, 3.5 units away from the line of reflection. On the other side, we go half, 1.5, 2.5, 3.5 units, and we get to this point. This point is 1.5 units away. We go half, 1.5, and we get to this point. This point is 1, 2, 3.5 units away, we go half, 1.5, 2.5, 3.5, we get to that point, and this point is 1, 2, 3, 4, 5, 6.5 units away from the y equals x line. Then we go half, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5, and we get to that point. So each of our points on y equals x squared plus 1 was reflected across the y equals x axis, which confirms that the relation that we have with the blue graph is the inverse of the function y equals x squared plus 1. Is the inverse a function? No, the inverse would not be a function because it does not pass the vertical line test. We could also tell this by looking at the original function. It doesn't pass the horizontal line test, so then the inverse of that function will not be a function. B, f of x equals 2x minus 6. We can write it as y equals 2x minus 6. For the inverse, we switch x and y, so x equals 2y minus 6. Then we have to isolate the y, so add 6, we get x plus 6 equals 2y. Divide everything by 2, and we get y equals 1/2 x, or x divided by 2, doesn't matter, plus 3. Draw the original function f of x equals 2x minus 6. That's a y-intercept of -6, and then a slope of 2, which is 2 over 1. So positive 2, up 2, right 1, up 2, right 1, up 2, right 1, etc. And I can join those points with a line. I can also go down to left 1 to get some more points. That's our function f of x equals 2x minus 6. Then we can graph the inverse, which is 1/2 x plus 3. That means a y-intercept of 3, and then a slope of 1 over 2, so positive 1 over 2, up 1, right 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 2, or down 1, left 2, down 1, left 2, down 1, left 2, down 1, left 2, down 1, left 2. Join those points with a line. To verify if this for sure is the inverse of our original function, we can either switch the x and y values of points on the original function to see if we get the points on the inverse function, or we can check the reflection across y equals x. I see that the point that's on the line of reflection is a point on both graphs, so it's an invariant point, doesn't change, so that is correct. Take a few other points. This point, for example, on the original is 1 away from the line of reflection. Go 1 away on the other side, and we get to this point. This point here is 1, 2 away. Go 2 on the other side, and we get to that point on the inverse. This point is 1 away, go 1 on the other side, and we get to this point. So we can confirm that y equals 1/2 x plus 3 is the inverse of our original function. Is our inverse a function? Yes, it would pass the vertical line test. Or we could say that the original function f of x equals 2x minus 6 would pass the horizontal line test. So we know that the inverse is a function. So we can write it as f inverse x equals 1/2 x plus 3. Example, the function f of x equals a bracket negative x cubed minus x plus 2 has an inverse such that f inverse of 6 equals negative 2. Solve for a. If f inverse 6 equals negative 2, we know that for inverse we switch the x and the y value, so then for f of negative 2, that would have to equal 6. Then we can calculate f of negative 2, which would be a bracket negative 2 cubed minus negative 2 plus 2. The value of f of negative 2 is 6, so now I can put 6 equals a and then calculate negative 2 cubed is negative 8. Negative 1 times negative 2 is plus 2, and then plus 2 again. Then we have 6 equals a. Negative 1 times negative 8 is 8 plus 4. Then we have 6 equals a times 12. Divide both sides by 12. And we get a equals 1/2. Summary. The inverse of a relation can be found by interchanging the x and y coordinates of the ordered pairs of the relation. The inverse of a relation can be found by reflecting the original relation in the line of y equals x. If the inverse is a function, it can be written as f inverse x. The domain of a function becomes the range of its inverse, and the range of the function becomes the domain of its inverse. The x and y intercepts are interchanged. We didn't really talk about that, but we can see that here. So we have a y-intercept here at 1, which on the inverse becomes an x-intercept at 1. Here we have an x-intercept at 3, which becomes a y-intercept on the inverse. And on the original we have a y-intercept of negative 6, which becomes an x-intercept on the inverse. And lastly, invariant points lie on the line y equals x. That brings us to the end of the Chapter 1 notes.